This is Lab 3 Magnetic Field of a Bar Magnet. The purpose of this lab is to measure the magnetic field due to a small bar magnet and find the magnetic dipole moment of a bar magnet using the distance dependence of magnetic fields. Our preview of the results of the magnetic dipole moment is this, N is this, and then we have the observed and predicted magnetic field as shown. Our fundamental principles include the Biot-Savart's law, which is the magnetic field of a single charge, and then we have the magnetic field of a dipole on and off axis as shown here, which we will use in our code, and the magnetic dipole moment on is shown right here, and then we have the magnetic field on axis right here, and the distance dependence formula shows how the field falls off with increased distance. These three formulas we will use later to solve for Kn and the magnetic dipole moment. Our models include the magnetometer sensor as the system and the surroundings as everything else. Our procedure, we have to first find the sensor location, which first we find where the x-axis magnitude is 0, mark that with tape, and then find where the magnitude is 0 on the y-axis and mark that with tape, and the intersection in this corner right here is the sensor. So first we then find the observed and predicted magnitudes of the off and on axis magnetic fields. So this is the off-axis magnetic field, and then this is the on-axis magnetic field. So we use code to model, to determine and visualize the value of the magnetic dipole moment of a bar magnet. We also assume that bar magnets act as a magnetic dipole. Magnetic field gets closer to 0 as distance increases. Only the magnet and the Earth's magnetic field are at play. Magnetic field and moment go the same direction, and the net magnetic field in Atlanta is this number right here. So this is our on-axis data, and this is the average. This is the linearization of the averages of the fields, and then this is the off-axis field data that we have. And this equation here we will use, it is the same as this right here, and we'll use this to find N and K. So our observations are when the magnetometer is far away from the magnet, it measures a near zero magnet field in the x direction. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. So our calculations are that N equals the slope, as we see right here, K equals the e to the power of the y-intercept, and the magnetic dipole moment observed is this number right here, as we set these two equal, and since we found K and N from comparing these two equations, we can find the magnetic dipole moment, which is that number right there. And then we have the magnetic field observed, which we got from this data down here. And then we have magnetic field predicted, which we got from the code, which is right here. So this shows us the magnetic field as a visualization. We have the magnetic field predicted, as shown here. So the first thing that we have to do for our code is we have to insert our magnetic dipole moment, which we calculated earlier. We stick it right there. And then we have to create a function for the magnetic field, which we use this formula from earlier, because this works for on and off axis magnetic field. And then this is us making all of the arrows for the on axis, which is the orange arrows, the off axis are the blue arrows, and the purple arrow is the perpendicular distance, which is shown here. So our dperp we got from our data from earlier, and then we used our function that we made to find the magnetic field of from that point, and then made an arrow to show that. So that's that purple arrow over here. So then our potential error for this lab is quite a few. So other electronic devices could have skewed the data. The exact location of the sensor could have been off. The phone could have not stayed on axis exactly, and then arrows in compensation for the magnetic north could have occurred, and then rounding errors could have occurred. So what if? What if you hadn't oriented your phone to compensate for the magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? Well, the Earth's magnetic field would interfere with the results more so than it might have already due to errors, as it would interfere with the bar magnet's magnetic field and skew the results, because for this lab we are compensating, or we're trying to compensate for the Earth's magnetic field so that it's not at play with the bar magnet. But if we would have it at any axis, then the Earth would have some value that would be unknown to us, and so we wouldn't be able to tell what the actual bar magnetic field is. So, and then what if you were to stick two identical magnets together into N and run the experiment again? So the values would most likely just be about 2 times larger, but it would be the same pattern and relative shape, so all the arrows should be in the same direction. It should just be a lot larger, a lot bigger. Yeah, thank you.